Hello students, we have already seen a case where a line can touch or intersect a circle in one point. This point is called point of contact and the line is called tangent. So the natural question is, who called this line as tangent and why? But first let us define tangent. A tangent to a circle is the line that passes through the circle at only one point. Now let us answer our questions. For that, we will have to go back in 1583 AD to the University of Copenhagen. In this university, there was a mathematics professor named Thomas Finke. What he first observed was that when a line intersects the circle in only one point, it looks like that it is just touching that circle. So he called this line as tangent, which is derived from a Latin word tangere or tangere, which means to touch, as tangent looks as if it is touching the circle, but it is also intersecting the circle at that point. Now students, you must have observed tangents in real life also. If not, then just look around you. I'm sure you have seen a bicycle or a cart moving on the road. Look at the wheels of these vehicles. We see that their path on the road is a straight line path. Now if we consider this wheel as a circle and their path as a line, we notice that it behaves like a tangent to the circle. Now rotate this wheel. We'll see the situation is still the same, but just the point of contact has changed. If we keep repeating this, we see that whatever the position of wheel is, it will always have only one point in common with the road. Now see the spokes of the circle. They act like a radii of that circle, isn't it? Yes. You'll also see that they are making some angle with the road. If you measure this angle, you'll find it to be 90 degrees. Thus, a tangent and a radii will always have a 90 degree between them. Remember students, this is very important property of tangent, that it is always perpendicular to the radius of the circle at the point of contact. But is this always true? Let us see is it true or not. We also saw property of a tangent, that it is always perpendicular to the radius at that point of contact. In simple words, when radius is drawn at a point of contact of a tangent in a circle, they both have 90 degrees. Now we shall prove this property. How? Let's see. We have a theorem to prove this property, which says the tangent at any point on a circle is perpendicular to the radius through the point of contact. So what we are given here? A circle with center O and tangent xy at a point P, which is nothing but a point of contact. We need to prove that OP is perpendicular to xy. For that, we shall do some construction first. Take a point Q on xy other than P and join OQ. You can see it intersects the circle at point R. So let's see the proof. But before that, let us recall some concepts that you already know. We'll use these concepts for our proof. Take one line segment, let us say AB. Take a point P on it. Now mathematically, this situation can be represented as A dash B dash B. We can also say that length of whole line segment AB will be sum of the two parts of it that is AB is equal to AP plus PB. This implies that AB will be always greater than its two parts AP and PB. Here in our case also, we have a situation similar to this. Consider a line segment OQ which touches the circle in point R. So this can be represented as O'(R')Q. So can I say OQ is equal to OR plus RQ? This means OQ will be greater than both OR and RQ. Now we also know whenever the distance is shortest, it is always perpendicular. So now with these two concepts in consideration, let us see our proof. Now consider the point Q on xy other than P. Join OQ. Now this point has to lie outside the circle because if Q lies inside the circle, the xy will become a secant to that circle. This we have already seen. Thus, Q lies outside the circle for xy to become a tangent to that circle. Now points PR lie on the circle, therefore OP and OR are the radii of the circle. Therefore, can I say OP is equal to OR? Yes. So we see here that OQ is equal to OR plus RQ. This we have already seen because it is O'(R')Q. Therefore, OQ is greater than OR. This implies that OQ is also greater than OP since OP and OR are radii. So they are same. Since this happens for every point on the line XY other than the point P, that is point of contact. Thus, OP is the shortest distance of all the distances of the point O to the points of XY. Thus, we can say OP is perpendicular to XY. As we have already seen, shortest of all distance is always perpendicular. Thus, the theorem is proved that the tangent at any point on a circle is perpendicular to the radius through the point of contact. Here, our tangent xy is perpendicular to radius OP at the point of contact P. Thank you.